Hello, everybody, and welcome to another wonderful day of PCAM. So before we dive headfirst into infrared spectroscopy, I want to take a quick moment and review everything we learned way back in Chapter 7 about vibrational motion. So when we're going to do spectroscopy, what we're really going to be looking at is the amount of energy it takes to move in between energy levels for a molecule trapped inside of a potential well. The traditional treatment of this potential well is I've got one atom moving in a stationary field caused by the other atom. So it can go closer or further away, bouncing back and forth. And the potential well is going to tell me a lot about how easy that movement is. Now, it is worth noting this potential well is kind of a complex equation. So what we're going to be doing is trying to determine the energy levels using a power expansion. So this can be put out to any number of terms. However, we're going to be mostly focusing in on the first and second term. So a first and second order approximation of this method. As you've seen in lab, you can take it up to third or fourth order terms, but we can encapsulate most of the behavior we need from these first two terms. Now, again, we're going to be working with a potential well in terms of wave numbers because we're mostly going to be interested in spectroscopic techniques. So we want to care about how far apart these systems are in wave numbers because that's how we tend to measure the light. Now, the other important thing I want to make note of is that we're going to be denoting where each of these energy levels occurs using the vibrational quantum number. So the system will start off at 0. So we'll have our first state will be the ground state or 0 state. And then a V of 1 is the first excited state, second excited state, third excited state, and so forth. So let's go ahead and examine the energies of each of these states. Easiest way to do this, and honestly one of the most commonly methods employed, is the good old-fashioned harmonic oscillator. We assume that our molecule is vibrating back and forth inside of a quadratic potential well. This actually works fairly well for fairly low vibrational states, as the system is fairly quadratic down there at the bottom of the well. This also generates a very easy equation to get at the energy of the molecule, as we're only going to have a dependence upon what we call the vibrational constant, and of course, the energy level itself. Now, the vibrational constant is going to depend on what's called the vibrational frequency. So this is more or less going to be how fast the molecule is moving back and forth inside the potential well, essentially the speed of oscillation. And then correcting for units using the speed of light. Now, the vibrational velocity in turn can be given by the force constant, which is telling us about the curvature of the well, and the reduced mass. So essentially, how heavy is the effective mass of the molecule vibrating. And what we're going to see is that the heavier the molecule is, the slower it's going to move. Not too surprising. Slower it moves, more tightly packed. My energy levels are going to become much more tightly packed. Conversely, if I have a larger force constant, this means I'm going to have a very steep bond. My well is going to be very narrow, and this is going to push my energy levels further apart. Now, one of the other things I do want to make note of is that each of our vibrational levels will have a steady separation of the vibrational constant, and consequently, this means that the separation of energy levels, which should help dictate our vibrational spectra, is going to almost be exclusively dominated by this force constant and reduced mass. Also, as a quick reminder, molecules are always in motion. So even if I'm at my ground state of V of 0, I'm always going to have some energy embedded in that vibrational motion, which does play a key role. Always worth noting, molecules never stop moving. However, it is worth noting these energies are just a simple first approximation. You can see why we love these equations. They're very easy to work with. However, when we start working with higher vibrational levels, so I get closer and closer to dissociation, it's going to be more important to pick up extra terms from that power expansion. So the one we're typically used most often is the quadratic term, which brings in something called the anharmonicity. So our anharmonicity is simply going to be kind of a measure of how wide the well gets as I go further up into my vibrational states. Now, it is worth noting that our anharmonicity is going to have a relationship to the separation of my energy levels, again, under this ideal harmonic oscillator approximation, and essentially the well depth. So our D here is going to be our electronic disassociation energy. So how far the difference in energy from going from the very bottom of the well to essentially where my potential well essentially asymptotes off and I can break the system. Now, one of the things you can see is that what will end up happening as my uh, anharmonicity increases, the well becomes essentially wider. It's also going to become shallower because in order to get this number to go bigger while keeping the vibrational constant the same, I have to make the well shallower. So as a result, the anharmonicity can also be a measure of the depth of the well. However, this does bring an important point. While it is a natural tendency to refer to the stability of a molecule using the vibrational constant, that doesn't quite encapsulate everything. To truly capture stability, you need to have both of these constants together or the well depth, which actually brings us to a last important feature, which is in order to truly understand this system as a whole, I really need to go back to my full Morse potential. So this is the potential form we use to describe the entire well. So this will give us a lot of information about the stability and how much movement the system has. Big thing to note here, we have an A or alpha term, which is making use of our reduced mass, our well depth, and the vibrational frequency. So it has a lot of that information of the vibrational frequency embedded in that width. However, the other important feature that I want to bring up is again the importance of that electronic disassociation energy to give us the depth. But I do want to bring in one quick reminder that since molecules are always moving, we never really are at that bottom of the well. So if you're trying to determine the actual or realized disassociation energy, this electronic is kind of a nice ideal and a hand wavy number. In truth, we also are going to want to account for the energy of my ground state. So the more useful feature, essentially experimentally, is going to be this 0 point disassociation energy, which can be simply taken as the difference in between the ground state energy and that 0 point energy, which can be treated as either 1/2 the vibrational constant minus 1/4 the anharmonicity times the vibrational constant, or more commonly truncated, partially because the anharmonicity tends to be fairly low, as just 1/2 the vibrational constant, which means I just use the harmonic oscillator. So next time, we're going to take these basic equations and we're going to apply them to real vibrational spectroscopy once we've implemented our selection rules. Till then, take care.